So let's go ahead and get started with the module and building the transform itself in PyTorch. So let's just go ahead and import the relevant modules, torch, pandas, and numpy. So let's go ahead and create our transformer class and initialize it. Okay, so some of the parameters that we need to pass in is going to be your embedding, vocab size, your output size, your hidden size, and whether or not we're using CLS. So we're going to go through it one by one. So embedding is going to be each of these tokens, which dimension are we going to embed it to. So for example, we have batch size and sequence length. We're going to see which each of these tokens is going to be projected to which size embedding. So it's going to be batch size, sequence length, and embedding. So this is hyperparameter that you get to choose and to see which dimension that you wish to project it to. Now for vocab size, this is basically your number of unique words that you're going to have in a sentence. And why is this important? So example, let's just use an example. I love to go. Okay, so here we have 4 unique words. So what you're going to have to do is going to have to understand how embedding actually works. Each embedding has to understand the number of unique words. For I is going to be projected to a certain vector, love is going to be projected to a certain vector. So we're going to make use of PyTorch's and then embedding, which has to have a number of embeddings, which is the size of the dictionary of embeddings, and your embedding dimension, which you set it to 3. So here we're going to use an then embedding, which is going to be 4 unique words projected up to your size 3 embedding that we wish to set earlier. Then output size is basically after you're done for self-attention and you get output, what is the output that you actually want. So for classification, we maybe set it to 2. And your hidden size is basically doing a self-attention, what is the dimension of all the query, key, and value matrices that we're going to form. And this is again up to us to set. And use CLS is basically if we wish to append a token, the CLS token, and use this for classification, or if we don't, then we're going to use an averaging or some other logic that we can set later. Another key thing that we can do is actually go ahead and actually set default values that we can actually use. So example, you want to set if you're going to commonly do classification tasks, then we just set it to 2. And for hidden size, we're just going to set it to 32, and we probably want to use CLS most of the time, so we're just going to set it to true. Okay, so let's go ahead and actually initialize our super class, which is needed for basically all new NN dot modules. Okay, and let's actually go ahead and initialize some of the variables that we can actually go ahead and use it later on. So self.embedding equals to embedding, hidden size, and whether or not we're going to use CLS or not. And suppose that we do use CLS, remember we start off with batch size of just sentences, right? And for example, we just have a sentence I love, and maybe we want to actually append a CLS token I love, and we want to do this for every single sentence itself. So we have a CLS token for all the different batch sentences. So we're just gonna initialize our variable first, our CLS token. So we're going to use torch.ran and 1 embedding. Okay. The reason why we do this is that once we actually get a parameter of 1 embedding, we can just append it to other batch along the sequence length. So example, we have batch sequence length embedding, and then we add our CLS token. and we're just gonna along the sequence length dimension, we're just gonna add a CLS token, so it's gonna be +1. But another thing to make sure that importantly remember is CLS token is a trainable token, so we just can't pass in a randomized thing that we can't train. So we're gonna initialize it as a parameter itself. Okay. And then we're going to initialize our embed itself, the embedding earlier of, and then embedding. So we're going to pass in our vocab size and our actual embedding. So let's go ahead and initialize our self-attention logic and the modules, I mean. So we're going to create our query matrix of linear, embedding, and hidden size. And why we do this, recall, at this point, before we get to self-attention, we have batch, sequence length, and embedding. But we want to project it up to a hidden size matrix or query, key, and value. So we're going to multiply by WQ, and it's going to give us our hidden size. And to actually get to this part, WQ must be a size embedding hidden size, right? So we're just going to do that for WK as well. So copy and paste, because it's practically the same size matrices. Then finally we have our softmax. So once we get our attention weights, we have to normalize it and softmax it. And we're going to do this along each row. And finally, we have our fully connected layer to project the output to whatever classification or whatever task we have. So for now, we're going to project it to a size of 2, so either positive or negative, right? So at this point we have batch, size, hidden size, and we want to project it to output size. Specifically, we're actually going to extract out the CLS token, but we go through that in the for. Okay, so we're going to actually go through the forward method. And the forward method is where your input basically passes through the entire logic itself. So this is pretty much the most important part that we have to understand and helps you to clarify how the actual transformer works. So we have an input X, which is of size, batch, and sequence length. Okay, so basically it's like your, if we're going to use example, I love to go. So basically, we just want to start with the sequence length, and now we need to embed it. So now remember, we have I love, so we have, and to go, so we have 4 unique words, and we want to embed it to a dimension of 3. So remember, we initialize this self.embed, which takes up the vocab size and embedding. So vocab size here is likely set to be 4, and embedding is set to 3. So we're just gonna do that first and embed it with X, and we get the new input. So now it's going to be batch, sequence length, and embedding. Okay, so once we're done with this, remember we still have a CLS token that we still haven't accounted for. So if we're going to use CLS, we're gonna append it to each of the sequence. So this is where things we start to get a bit confusing. So let's just go through it first. So we got batch and sequence length and embedding. And now we want to append a CLS token along sequence length. And remember, the self.cls was a size of 1 1 embedding. Okay, so the idea is we're going to take the original and we're going to append 1 1 embedding, but it's likely not possible, so we have to project this 1 1 embedding up to batch size first. So we have common batch, sequence length, and common embedding, and we're going to get batch, sequence length plus 1 embedding. So the important thing is we have this parameter here that we have to first broadcast it batch number of times. So let's just go ahead and get batch size. Let's just keep it in our variable first. First we're going to get self.cls.expand, and we're going to expand it along the batch size. -1, -1, because those could just automate it. So importantly, we just need to broadcast it up to batch size, and it's going to be 1, and this is going to be embedding. Okay, and then we're going to use torch.cat to basically concatenate this expanded CLS token with the current input itself. And we're going to do this along the dimension of 1. Where dimension of 1 is basically your sequence length. We don't want to concatenate with embedding or sub-batch. We just want to concatenate with sequence length, and that's going to give us basically our new input. Okay, so now we expect the size to be batch, sequence length, and embedding. So that's pretty much it. Now let's move on to our query key and values. So let's just go ahead and pass it through our linear layers. And why does this work? Recall that everything now is batch, sequence length, embedding. We're going to project it to, we're just going to call it sequence length at this point, to hidden size. Then we're going to get our attention scores, which recall is basically query multiplied by key transpose. But you have to remember the size now is batch, sequence length, hidden size, and we logically want this hidden size and sequence length equals to sequence length. Just to make sense of it, it's basically every token now has like a weight of every other token. So that's why every sequence length has a sequence length vector. So how do we actually do this? Is remember we want to take a transpose, but we can't just put a dot t like numpy. We have to actually specify that we have to flip around sequence length and hidden size. So we're just gonna attention scores equals the query cross multiply with key.transpose -2 and -1. So as simple as that. Now we're going to get batch, sequence length, and we want to normalize it. So we get that hidden size and the square root of it. And now we're going to get self.hidden size. Now we're going to get the normalized, the softmax version of it. So we're going to use self.softmax of attention scores. And finally, we're going to get our output here to attention weights multiplied by value. So what we expect now, remember, we have sequence length to sequence length times value is going to be sequence length and hidden size once again. So now every vector now has a weighted sum of the values, and hence every vector in sequence length has a hidden size back. So now back to the actual logic itself. If we use CLS we use CLS hidden size to classify. Else we use the average of all the tokens. So if you use CLS, then CLS representation, which is going to be our output that we're going to use, is going to be output 0 equal. So we're going to extract out basically the first token hidden size, and the size of this is going to be batch and hidden size. So basically you get rid of the sequencer because you're just going to extract the first one. Else CLS representation is going to be output.mean of output.mean along the first dimension. So this is also going to be batch hidden size. So we can finally put it through our fully connected layer or CLS representation, and this projects it up, project it down, sorry, to output size of 2, which is going to be output size. And that's pretty much our transformer that we implemented, and we're going to move on to basically just dummy values, and just going to do a dummy training as well, just to understand how the output. Okay, so let's actually start with the training model of this input transform that we created. So we're just going to use a sample input and output here. So we're going to randomly generate our x and y values just for the sake of demonstration. So here we're going to use a sequence select of 16, embedding 128, batch size of 64, hidden size 128, and vocab values of 4. So x, we're just going to use torch.ran in between 0 and vocab values in the size of batch size and sequence length. So here y is just going to be a vector of size 64 in the range of either 0 or 1. So it's just going to be zeros or ones. And the reason for this, we go through it soon. So let's go ahead and initialize our simple transformer with embedding size of 128, vocab values of 4, output size of 2, and hidden size of 128. And just going to check what it outputs. So just passing x into our model and print out the first 5 rows. So here it predicts the first row with high probability. So basically the larger value is what's going to be the probability. And here it predicts the first label here. Here it predicts the second label, and here it predicts second label, and here it predicts the first label. So how we can do this, we can check with using argmax, just passing the output here along the row dimension, basically the last dimension, and we get a bunch of ones and zeros and ones. And this basically predicts, okay, maybe 1 is positive, 0 is negative, 1 is positive, and this is based on the training data later of y, which is a size 64, again, either zeros or ones. So we compare this output with y to get our loss. So how to check the actual number of predictions they made? Well, we can take this equals to y. Now that gives us either bunch of trues and falses. So true evaluates to 1 and false evaluates to 0. So this way we can take a sum, take the item from the tensor to get a number of actual predictions, to get 32. So we're going to use loss function of cross entropy loss, and cross entropy loss expects a model x, so basically going to be a batch of classes, with compare it with results y, which is going to be a batch size. And you're going to use this optimizer, the Adam optimizer, with learning rate of 0.001. So let's actually start our training. So let's just do it for about 100 epochs. So fine range epochs. Then first, very importantly, we have to zero grad it, so it does not accumulate the gradients over the training. And the actual output itself. And let's actually calculate the loss using a loss function. So y predict and actual y. We're going to back propagate it using this loss function. And we're going to update our weight of the transformer so it actually learns. So optimize the step. So this actually is pretty much the training, but we actually want to see what's the accuracy so far. So let's actually initialize correct and total. So total will basically be our length of y predictions. At correct, remember, from this part here, the torch.argmax equals y. We're just going to use the same logic here. Get the sum and the item, and we're going to print the epochs every 10, actually 20. And see if it works. Come on, but this should be y prediction, so let's go ahead and change that and run it again. And yeah, technically it does train well, but as you can see, it doesn't go past 0.6875 because after all, this is using pretty much meaningless data with very little data space, and we have to use proper data. But the idea is that it managed to improve a bit, and we will see this with proper data soon using IMDb dataset. So that's pretty much for the training of this simple data transformer, just to see how it works, just to see how the input and output format is. So yep, thanks for watching.